Tonight, we're going to confront one of the hardest truths about the universe. Humanity has dreamed about traveling to the stars for centuries. We've written countless stories about it, made films, built entire universes of science fiction around the idea. But here's what the physics actually tells us, what the mathematics reveals when you work through the numbers carefully. Interstellar travel isn't just difficult or expensive or requiring technologies we don't have yet. It might be fundamentally impossible in any practical sense. And by the end of tonight, you're going to understand exactly why the universe has imposed limits that we cannot overcome, no matter how advanced our technology becomes. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The dream of interstellar travel feels so natural to us. We look up at the night sky and see thousands of stars. They seem close enough to reach, scattered across the darkness like cities on a distant shore. Our species has always been explorers. We crossed oceans, climbed mountains, eventually reached the moon. Every barrier we encountered, we eventually overcame. The Pacific Ocean seemed impossibly vast to ancient humans, but we crossed it. The sound barrier seemed insurmountable, but we broke it. The moon was literally another world, and we walked on it. So naturally, we assume the stars are just the next step. A harder challenge? Sure, but ultimately achievable with enough time, resources, and technological development. But there's a fundamental difference between every challenge humanity has overcome and the challenge of reaching another star. Every previous barrier was a limitation of our technology, our knowledge, or our capabilities. Interstellar travel is limited by the laws of physics themselves. And those laws don't change, don't negotiate, don't care about our ambitions or our dreams. Let's start with the most basic problem: distance. The nearest star to our Sun is Proxima Centauri. It's part of a triple star system called Alpha Centauri. Proxima Centauri is 4.24 light-years away. That's the closest star we have, our nearest stellar neighbor, and it's 25 trillion miles distant, or 40 trillion kilometers. To put that in perspective, when the Voyager 1 spacecraft launched in 1977, it was one of the fastest things humans had ever sent into space. It's been traveling for over 45 years. It's now the most distant human-made object, farther from Earth than any other spacecraft we've built. It's currently about 14.5 billion miles from the Sun, or 23 billion kilometers. That's roughly 1/56th of 1% of the distance to Proxima Centauri. In over 4 decades of continuous travel, Voyager 1 has covered less than 1/200th of the distance to the nearest star. At its current speed, Voyager 1 would take about 75,000 years to reach Proxima Centauri if it were headed in that direction, which it isn't. 75,000 years. Human civilization is only about 10,000 years old. Agriculture began roughly 12,000 years ago. The earliest cities emerged around 6,000 years ago. The pyramids of Egypt were built about 4,500 years ago. A journey to the nearest star at Voyager's speed would span a time frame longer than all of recorded human history. You might think, well, we just need to go faster. Build a faster spacecraft. After all, Voyager 1 was launched in the 1970s with technology that's ancient by modern standards. Surely, we can do better now. And you'd be right. We can build faster spacecraft. The Parker Solar Probe, launched in 2018, is currently the fastest human-made object ever built. At its peak speed, diving close to the Sun and using solar gravity to accelerate, it reaches about 119 miles per second. That's about 0.064% of the speed of light. At that incredible velocity, over 430,000 miles per hour, it would still take about 6,600 years to reach Proxima Centauri. 6,600 years. Still far beyond anything resembling a practical journey. So, the obvious solution seems clear. We need to go much faster. Not just a little faster, but dramatically faster. We need to reach a significant fraction of the speed of light. Say, 10% of light speed, or even better, 50%. At 10% of light speed, the journey to Proxima Centauri would take 42 years. Still a lifetime, but at least conceivable. At 50% of light speed, the trip drops to about 8.5 years. Now, we're talking about something that seems almost manageable. A long journey, yes, but within the span of a normal career. The problem is getting to those speeds. And this is where the physics becomes brutally unforgiving. Let's talk about energy. Energy is the fundamental currency of the universe. Everything that moves, everything that happens, requires energy. And the amount of energy required to accelerate an object increases with both the mass of the object and the speed you want to achieve. For slow speeds, the relationship is simple. Kinetic energy equals 1/2 mass times velocity squared. Double your speed, and you need 4 times the energy. Triple your speed, and you need 9 times the energy. But that's only at slow speeds. Speeds that are a tiny fraction of light speed. When you start approaching significant fractions of the speed of light, special relativity kicks in. And the energy requirements don't just increase, they explode. As you get closer and closer to light speed, the energy required approaches infinity. You cannot accelerate a massive object to exactly the speed of light. It would require infinite energy. The speed of light is a hard limit, an absolute barrier that nothing with mass can cross. Let me give you some actual numbers to show how devastating this becomes. Let's say we want to send a small probe to another star. Not a massive spaceship with life support and crew quarters and supplies. Just a tiny probe, maybe the size and weight of a small car. About 1,000 kilograms. That's 2,200 pounds. We want to accelerate this probe to 10% of the speed of light. Just 10%. Not even close to light speed, but enough to make the journey to Proxima Centauri in about 42 years instead of thousands. How much energy would that require? The kinetic energy of 1,000 kilograms moving at 10% of light speed is approximately 4.5 times 10 to the 17th joules. That's 450,000 trillion joules. To put that in perspective, that's roughly the total amount of energy humanity currently uses in about 6 months. All the electricity, all the fuel, all the energy from every power plant, every car, every factory, every device on Earth for 6 months, just to accelerate a 1-ton probe to 10% of light speed. And that's just the kinetic energy the probe needs to have. It doesn't account for the inefficiency of any propulsion system. No propulsion system is 100% efficient. Most are far less than that. Chemical rockets, the kind we use now, are maybe 3% efficient in converting fuel energy to kinetic energy. Nuclear rockets might reach 10 to 20% efficiency. Even the most optimistic theoretical propulsion systems, things that don't exist yet and might never exist, probably can't exceed 50% efficiency. So, realistically, you'd need at least twice that energy, probably more like 10 times that amount, depending on your propulsion technology. We're talking about energy requirements equal to significant fractions of humanity's total annual energy production, just to send a tiny probe to the nearest star. And it gets worse when you scale up, because kinetic energy is proportional to mass. If you want to send a spacecraft 10 times heavier, you need 10 times the energy. A modest interstellar spacecraft carrying people would need to be much more massive than a 1-ton probe. It would need life support systems, radiation shielding, food and water for the journey, living quarters, equipment for the destination, fuel for maneuvering and slowing down. A realistic crewed spacecraft would probably mass at least several hundred tons. More likely, thousands of tons. The International Space Station masses about 420 tons, and that's just a habitat in orbit, not a self-contained ship designed for decades of interstellar flight. The ISS requires constant resupply from Earth. Water, food, spare parts, equipment. Every few months, cargo ships arrive from Earth, carrying tons of supplies. An interstellar ship can't be resupplied. It needs to carry everything for the entire journey. That means growing food on board, recycling water and air with perfect efficiency, manufacturing replacement parts from raw materials. All of that requires equipment, and equipment has mass. Greenhouses for growing food require lights, growing medium, seeds, water systems, climate control. Water recycling needs filters, pumps, chemical processors. Air recycling needs carbon dioxide scrubbers, oxygen generators, backup systems. Manufacturing capabilities mean machine shops, 3D printers, raw material stockpiles, smelting equipment. A true interstellar generation ship would probably need to mass tens of thousands of tons or more to carry everything needed for a multi-generational journey. Maybe 50,000 tons. Maybe 100,000. The more self-sufficient you want the ship to be, the more mass you need. And remember, we're not just talking about the ship itself. We need to accelerate all that mass to a significant fraction of light speed. Scale up from our 1-ton probe to a 10,000-ton spacecraft, and suddenly you need 10,000 times the energy. 10,000 times 4.5 times 10 to the 17th joules. That's 4.5 times 10 to the 21st joules. To put that number in perspective, the total energy humanity used in the year 2020 was about 600 exajoules. That's 6 times 10 to the 20 joules. So accelerating a 10,000-ton spacecraft to 10% of light speed would require about 7.5 times humanity's entire annual energy production. Just for the kinetic energy, not accounting for propulsion inefficiency, not accounting for acceleration and deceleration. If we include those factors, we're looking at energy requirements equal to decades or centuries of total human energy production for a single ship to send it to one star. Now we're talking about energy equal to thousands of years of humanity's total energy production just for the kinetic energy alone. This isn't a matter of building better rockets or finding better fuel. This is fundamental physics. The energy is required by the laws of nature themselves. There's no way around it. And here's another problem nobody thinks about. Where does that energy come from? Currently, most of our energy comes from fossil fuels. Coal, oil, natural gas. We're burning through reserves that took millions of years to accumulate. And we're running out. At current consumption rates, known oil reserves will last maybe 50 years. Natural gas, maybe 70 years. Coal, a bit longer, perhaps 150 years. Even if we could somehow dedicate all of Earth's fossil fuel reserves to building an interstellar spacecraft, we wouldn't have nearly enough energy. What about renewable energy? Solar, wind, hydro, geothermal. These are sustainable, but the total energy available is limited. All the sunlight hitting Earth's surface amounts to about 170,000 terawatts. Sounds like a lot. But we can't capture it all. Not even close. Current solar panel technology is maybe 20% efficient. And you can't cover the entire planet with solar panels. People need places to live. Food needs places to grow. Ecosystems need space to exist. Realistically, we might capture a few percent of the total solar energy hitting Earth. That gives us a few thousand terawatts of power. Significant, but still nowhere near enough to accelerate massive spacecraft to relativistic speeds. Nuclear power offers more concentrated energy. Fission reactors split uranium or plutonium atoms, releasing energy. Current fission technology provides a decent amount of power, but uranium is also a limited resource. Known reserves at current consumption rates last about 90 years. You could extend that significantly with breeder reactors that produce more fuel than they consume, but even then, you're limited by the total amount of fissionable material available on Earth. Fusion, if we ever figure it out, offers more promise. Fusion fuel, primarily deuterium, can be extracted from seawater. There's enough deuterium in Earth's oceans to power human civilization at current levels for billions of years. But fusion power is still hypothetical. We've been working on it for 70 years, and we still don't have a working fusion power plant that produces more energy than it consumes. We might figure it out in the next few decades. Or it might remain perpetually 30 years away, always just beyond our reach. Even if we master fusion, even if we build an entire energy infrastructure based on fusion power, the total available energy is still limited by how many fusion reactors we can build and how fast we can produce fusion fuel. Building enough fusion reactors to generate the energy needed for interstellar travel would be a multi-century project requiring resources on a scale humanity has never attempted. We'd essentially need to convert our entire civilization into a spacecraft construction project. Every bit of available energy for decades or centuries dedicated to building and launching one ship. That means no energy for anything else. No powering cities, no running industries, no transportation, no agriculture beyond subsistence farming. The entire planet working toward a single goal. Is that realistic? Would any civilization choose to do that? Would any government convince its people to accept massive reductions in living standards for generations, all to build a ship that most people alive will never see completed, let alone see return any benefit? The political challenges are as daunting as the technical ones. You might think, what about antimatter? Antimatter is the ultimate fuel, right? When matter and antimatter meet, they annihilate completely, converting their entire mass to energy, according to Einstein's famous equation, E equals mc squared. It's the most efficient energy source theoretically possible. 100% conversion of mass to energy. Nothing can be more efficient than that. So, let's use antimatter. The problem is making antimatter. Antimatter doesn't exist naturally in any significant quantity anywhere we can access it. Every particle has an antiparticle counterpart. Electrons have positrons. Protons have antiprotons. When a particle meets its antiparticle, they annihilate in a flash of energy. Antimatter is real, not science fiction. We've created it in laboratories. Particle accelerators, like the Large Hadron Collider, produce antimatter regularly as part of their experiments. But the amounts are incredibly tiny. We're talking about nanograms, billionths of a gram. And producing even those tiny amounts requires enormous energy input. We can create it in particle accelerators, but the process is incredibly inefficient. Current technology requires roughly 10 billion times more energy to create antimatter than you get back when it annihilates. Let me repeat that. For every unit of energy you extract from antimatter annihilation, you had to spend 10 billion units of energy to create that antimatter in the first place. It's the worst energy trade in history. Antimatter isn't an energy source. It's an energy sink, a fantastically expensive way to store tiny amounts of energy. The inefficiency comes from basic physics. When you smash particles together in an accelerator, you create sprays of new particles and antiparticles. But only a tiny fraction of the collision energy goes into creating the specific antiparticles you want. Most of it disperses as heat, radiation, and particles you don't need. It's like trying to catch water from a fire hose with a teaspoon. Most of it misses. Current antimatter production at CERN creates roughly 1.5 nanograms of antiprotons per year. That's 1.5 billionths of a gram. If you could perfectly annihilate that with regular matter, it would release energy equivalent to about 40 kilograms of TNT. Not nothing, but hardly world-changing. And producing that nanogram required running massive particle accelerators, consuming megawatts of power for an entire year. Even if we improved the efficiency by a factor of 1,000,000, which would require physics breakthroughs we can't even imagine right now, it would still require 10,000 times more energy to make the antimatter than you'd get back from using it. Some people propose collecting antimatter from space. There are trace amounts of antimatter in cosmic rays and in certain astrophysical phenomena, but the amounts are vanishingly small, and collecting them would require equipment spread across enormous volumes of space. You'd spend more energy building and operating the collection system than you'd ever collect. Others suggest creating antimatter using solar power in space, where energy is abundant and free. Build massive solar arrays, use the power to run particle accelerators, gradually accumulate antimatter over years or decades. But the infrastructure required would be enormous. Solar panels covering areas the size of countries, particle accelerators in orbit, magnetic bottles to store the antimatter without it touching regular matter and annihilating. All of this would need to be built in space, which is currently far beyond our capabilities. And even if we built it, even if we ran it for decades, we'd still be fighting the fundamental inefficiency. The energy cost of creating antimatter is unavoidable given current physics. Antimatter isn't a solution. It's a way to store energy, and a devastatingly inefficient one at that. Unless we discover completely new physics, new ways to create or collect antimatter that bypass the current inefficiencies, it remains impractical for any large-scale application, let alone powering starships. What about nuclear fusion? Fusion is what powers the sun. It's the process of combining light atomic nuclei to form heavier ones, releasing energy in the process. When hydrogen atoms fuse to form helium, they release tremendous amounts of energy. This is how stars shine. The Sun converts about 600 million tons of hydrogen into helium every single second. Every second, 4 million tons of matter is converted directly to energy via E equals mc squared. That energy radiates outward as light and heat, making life on Earth possible. We've been trying to achieve controlled fusion for energy production for decades. It's incredibly difficult. The Sun does it by being enormous, with gravity compressing the core to temperatures of about 27 million degrees Fahrenheit or 15 million degrees Celsius, and pressures millions of times greater than Earth's atmosphere. Under those conditions, hydrogen nuclei are slammed together with enough force to overcome their electrical repulsion and fuse. On Earth, we can't use gravity to create those conditions. We don't have enough mass. Instead, we try to create fusion using magnetic fields to confine superheated plasma or using powerful lasers to compress fuel pellets. Both approaches face enormous challenges. The plasma in a magnetic fusion reactor wants to escape. It writhes and twists, touching the container walls and cooling down. Laser fusion requires precise timing and enormous power to compress the fuel pellets symmetrically. We've achieved fusion in experimental reactors. We can make it happen. But we've never achieved sustained fusion that produces more energy than it consumes. Not yet. Every fusion reaction we've managed has required more energy input than we got back as output. We're getting closer. Recent experiments at the National Ignition Facility achieved fusion ignition, where the fusion reaction produced more energy than the lasers delivered to the fuel. But the lasers themselves required far more energy than what reached the fuel. Most of the energy was lost as heat and inefficiency in the laser system. Net energy gain, counting all the input energy, not just what reached the fuel, remains elusive. Maybe we'll figure it out in the next few decades. The International Thermonuclear Experimental Reactor, ITER, currently under construction in France, is designed to achieve sustained fusion with a net energy gain by the 2030s or 2040s. Maybe it will succeed. Maybe it won't. Fusion has been 30 years away for the past 70 years. Let's be optimistic and assume we figure it out. We build fusion reactors that work efficiently. We build fusion rockets that can use this process for propulsion. Fusion rockets would be far better than chemical rockets. Chemical rockets work by burning fuel, creating hot gases that expand and shoot out the back. The exhaust velocity is limited by the temperature you can achieve and the molecular weight of the exhaust. For the best chemical rockets, exhaust velocities are around 2.5 to 3 miles per second. Fusion rockets could, in principle, achieve much higher exhaust velocities. Instead of chemical energy, you're using nuclear energy, which is millions of times more concentrated. A well-designed fusion rocket might achieve exhaust velocities of 3 to 5% of the speed of light. That's 5,600 to 9,300 miles per second. Thousands of times better than chemical rockets. But they still face the fundamental energy problem. To accelerate our 1,000 kilogram probe to 10% of light speed using a fusion rocket, you'd still need to carry fuel. And the fuel has mass. And that mass needs to be accelerated too. The fusion fuel would be deuterium and tritium, isotopes of hydrogen. Deuterium can be extracted from seawater. Tritium is radioactive and doesn't exist naturally in large quantities, but it can be bred from lithium using neutrons from the fusion reaction itself. So, fuel availability isn't necessarily a problem, but fuel mass is. This creates what's called the tyranny of the rocket equation. The rocket equation is a mathematical relationship discovered by Konstantin Tsiolkovsky in 1897. Tsiolkovsky was a Russian scientist who never went to university but taught himself mathematics and physics. He worked as a school teacher in rural Russia while conducting his scientific work in his spare time. He's considered one of the founders of astronautic theory. He worked out the fundamental mathematics of rocket propulsion decades before anyone actually built a rocket capable of reaching space. The equation he derived is deceptively simple. It describes how the change in velocity of a rocket depends on the exhaust velocity of the propellant and the ratio of the rocket's initial mass to its final mass. The equation is delta V equals V exhaust times the natural logarithm of m initial divided by m final. Delta V is your change in velocity, how fast you want to go. V exhaust is how fast your rocket can throw propellant out the back. M initial is the mass of the rocket when it's full of fuel. M final is the mass when the fuel is exhausted. Let's unpack what this means. The natural logarithm is a mathematical function that grows very slowly. To double the output of a logarithm, you need to square the input. To triple the output, you need to cube the input. This is the source of the tyranny. The critical insight is that the relationship is logarithmic. To get a big change in velocity, you need an exponentially increasing mass ratio. If you want to double your delta V, you don't just need twice as much fuel. You need the square of your mass ratio. Want to triple your delta V? You need the cube of your mass ratio. The fuel required increases exponentially with the speed you want to achieve. This is a fundamental limit that no amount of engineering cleverness can bypass. It's not a technology problem. It's a mathematics problem. The logarithm doesn't care how advanced your civilization is. Let's work through an example with realistic numbers to see how brutal this becomes. Suppose we have a fusion rocket with an exhaust velocity of about 3% of the speed of light. That's 5,600 miles per second. That's optimistic, but potentially achievable with a well-designed fusion propulsion system using deuterium-tritium fusion. The fusion reaction produces high-energy neutrons and helium nuclei. You'd need to capture that energy somehow, perhaps using magnetic fields to direct the charged particles, or using the neutrons to heat a working fluid that then expands out a nozzle. The engineering would be incredibly complex, but let's assume it can be done. 3% of light speed for exhaust velocity. Now, we want to accelerate to 10% of light speed. That's our delta V. 10% of the speed of light is 18,600 miles per second. Our delta V is 18,600 miles per second. Our V exhaust is 5,600 miles per second. Plugging into the rocket equation, we get 18,600 equals 5,600 times the natural logarithm of m initial divided by m final. Divide both sides by 5,600, and we get approximately 3.33 equals the natural logarithm of the mass ratio. To solve for the mass ratio, we take e to the power of 3.33. E is Euler's number, approximately 2.718. E to the power of 3.3 is about 28. That means for every kilogram of payload, we need 28 kilograms of initial mass. In other words, we need 27 kilograms of fuel for every kilogram of spacecraft. Our 1,000 kilogram payload would require a spacecraft with a starting mass of 28,000 kilograms. 27,000 kilograms of fusion, fuel to accelerate 1,000 kilograms of probe to 10% of light speed. That's a mass ratio of 28 to 1. That might not sound too bad. Modern rockets routinely have mass ratios of 20 to 1 or higher. The Saturn V that took astronauts to the moon had a mass ratio of about 50 to 1. Most of the rocket was fuel. The actual payload that reached the moon was tiny compared to the total mass that launched from Earth. So, maybe this is doable. But wait, it's worse. Much worse. That gets us to 10% of light speed. But when we reach the destination, we're moving at 10% of light speed. If we want to stop, to actually enter orbit around the target star or explore its planets, we need to decelerate. Slowing down from 10% of light speed to 0 requires just as much delta V as accelerating from 0 to 10% did. That requires just as much fuel as accelerating did. But here's the killer. We need to carry that deceleration fuel with us during the acceleration phase. So, we need another mass ratio of 28 to slow down. But now we're compounding the ratios. To accelerate and then decelerate, we need a total mass ratio of 28 times 28. That's 784. For every kilogram of payload, we need 784 kilograms of starting mass. Our 1,000 kilogram probe now requires 784,000 kilograms of spacecraft when fully fueled. 783,000 kilograms of fusion fuel to deliver 1 ton of payload to another star and have it slow down when it gets there. 783 tons of fuel for 1 ton of payload. And remember, that's with a very optimistic exhaust velocity of 3% of light speed. If your exhaust velocity is lower, the mass ratios get exponentially worse. At 1% of light speed exhaust velocity, which is more realistic for most fusion concepts, the mass ratio for accelerating to 10% of light speed would be about 22,000 to 1. For accelerating and decelerating, it would be 22,000 squared. That's 484 million to 1. You'd need nearly 500 million kilograms of fuel for every kilogram of payload. Completely impractical. Even at the optimistic 3% exhaust velocity, 783 tons of fuel per ton of payload is challenging. Where do you get that much fusion fuel? Deuterium can be extracted from seawater, but you need to process enormous amounts of water. Seawater contains about 33 grams of deuterium per cubic meter. To get 783 tons of deuterium, you'd need to process about 24 million cubic meters of seawater. That's 24 million tons of water. You'd need to build massive processing plants, consume huge amounts of energy, separating the deuterium from regular hydrogen, and somehow launch all that fuel into orbit. Tritium is even worse because it doesn't exist naturally. You'd need to breed it from lithium in nuclear reactors, which takes time and energy. And tritium is radioactive with a half-life of about 12 years. If your mission prep takes longer than a few years, you lose significant amounts of fuel to radioactive decay before you even launch. You'd need to continuously produce tritium right up until launch and possibly even during the mission. Most rocket equation calculations assume you can acquire and store your fuel relatively easily. For chemical rockets on Earth, That's mostly true. Gasoline and liquid oxygen are available. For fusion rockets in space, it's not true at all. Every kilogram of fuel would need to be laboriously produced and launched into orbit. At current launch costs of about $1,500 per kilogram to low Earth orbit, launching 783 tons of fuel would cost over $1 billion. And that's just the fuel. The spacecraft itself, all the life support equipment, radiation shielding, and scientific instruments would cost far more to build and launch. SpaceX has brought launch costs down significantly with reusable rockets. But we're still talking about hundreds of millions of dollars to orbit the fuel alone. And we haven't even discussed where the spacecraft is assembled. You can't build a 784-ton interstellar spacecraft on Earth and launch it as a single piece. It would need to be assembled in space from components launched separately. That means a space-based construction facility, robotic assemblers or human workers in spacesuits, logistics to coordinate dozens or hundreds of launches. The complexity spirals rapidly. And it gets even worse if we're realistic about what a crewed mission requires. We've been talking about a 1-ton payload, but a crewed spacecraft masses far more than 1 ton. Let's say we want to send 10 people to another star. Not a large crew, but enough for genetic diversity and to cover all necessary skills. Each person needs life support: oxygen, water, food, waste processing. A human needs about 2.3 pounds of food per day, or 1 kilogram, plus about 3 liters of water for drinking, cooking, and hygiene. For a 42-year journey at 10% of light speed to Proxima Centauri, each person needs about 15,000 kilograms of food and 46,000 liters of water. That's 46 tons of water per person. For 10 people, that's 460 tons of water alone, plus 150 tons of food. Over 600 tons just for food and water. And we haven't included oxygen, medical supplies, spare parts, tools, computers, communication equipment, scientific instruments, or the actual structure of the spacecraft. A realistic crewed interstellar spacecraft for 10 people would probably mass at least 5,000 tons. Maybe 10,000. Applying our mass ratio of 784, we'd need to start with 3.9 million tons for a 5,000-ton ship, or 7.8 million tons for a 10,000-ton ship. Millions of tons of fusion fuel. The entire spacecraft, when fueled, would mass as much as a small mountain. Launching that much mass into space from Earth is completely impossible with any foreseeable technology. You'd need hundreds of thousands of rocket launches. At 1 launch per day, that's hundreds of years just to orbit the components. The only way it could possibly work is if you built the infrastructure to manufacture fuel in space. Mine asteroids for water ice, extract deuterium, breed tritium using nuclear reactors in space, assemble the spacecraft in orbit using materials also mined from asteroids. That requires an entire space-based industrial civilization. We don't have that. We're nowhere close. Building it would be the work of centuries, requiring resources and coordination on a scale humanity has never achieved. This is the tyranny of the rocket equation. It doesn't care about your dreams or ambitions. It doesn't care how advanced your technology is. It's pure mathematics, and mathematics doesn't negotiate. To go faster, you need exponentially more fuel. To carry more mass, you need exponentially more fuel. And that fuel has mass, So you need fuel to accelerate the fuel, which needs more fuel, in a vicious cycle that quickly becomes absurd. This is why interstellar travel is so fundamentally difficult. It's not just that the distances are large. It's that the energy required to cross those distances at any reasonable speed is astronomical. And carrying that energy as fuel creates exponential mass problems that spiral out of control. Every additional bit of speed you want requires exponentially more fuel. And that fuel has mass, which you also have to accelerate, which requires more fuel, which has more mass, and on and on. The rocket equation is the mathematics of despair for anyone who dreams of traveling to the stars. You might ask, what if we don't carry the fuel? What if we beam energy to the spacecraft from somewhere else? This is the idea behind concepts like laser-pushed light sails. You have a very large, very thin sail, basically a giant mirror. You shine powerful lasers at it from Earth or from satellites. The photons from the laser bounce off the sail and transfer momentum, pushing the spacecraft forward. The spacecraft itself doesn't carry any fuel. All the energy comes from the lasers doing the pushing. This avoids the rocket equation problem entirely. The Breakthrough Starshot initiative is exploring exactly this concept. The idea is to send tiny spacecraft, each weighing just a few grams, to Alpha Centauri. They'd use ultra-thin light sails and be accelerated by a massive array of lasers based on Earth. The plan is to accelerate these probes to about 20% of light speed. At that speed, they could reach Alpha Centauri in about 20 years. It's one of the most realistic interstellar mission concepts anyone has proposed. And yet, even this faces enormous challenges. First, the laser array required would be gigantic. We're talking about a ground-based laser system with a combined power of about 100 gigawatts. That's roughly 100 large power plants worth of energy, all focused into a laser beam. The beam would need to be aimed with incredible precision to hit a sail that's meters across from millions of miles away. And you'd need to keep the beam on target as the spacecraft accelerates to a significant fraction of light speed. The slightest aiming error and you miss the sail entirely. The spacecraft drifts off course and the mission fails. Second, the light sail would need to be incredibly light and incredibly strong. It would need to survive the intense laser bombardment without being vaporized. It would need to reflect the laser light without absorbing it, because any absorbed energy becomes heat. And in the vacuum of space, there's no air to carry heat away. Materials science might be able to solve this, but it's at the edge of what's theoretically possible. Third, these would be tiny probes, a few grams. That's lighter than a smartphone. You can't fit much into a few grams. Maybe a camera, a radio transmitter, some basic sensors. That's about it. No life support, obviously. No human crew. No ability to stop at the destination because there's no fuel and no way to slow down. These probes would fly past Alpha Centauri at 20% of light speed. They'd have maybe a few hours in the vicinity of the star system. They'd take whatever observations they could during that brief flyby. Then they'd continue into interstellar space forever, never to return. Fourth, communication is a massive problem. At 20% of light speed, the probes would reach Alpha Centauri in about 20 years. But the radio signals they send back travel at light speed. So, those signals would take another 4.24 years to reach Earth. Total mission time from launch to receiving the first data would be about 24 years, a quarter century. And the probes would be transmitting with tiny radios, powered by tiny batteries or tiny solar panels. The signal strength would be incredibly weak. We'd need massive radio dishes on Earth to pick up those faint signals from across 4 light-years of space. Fifth, and perhaps most critically, even the breakthrough starshot concept requires technologies we don't have. The laser array doesn't exist. The light sail materials don't exist. The tiny spacecraft with all the required capabilities don't exist. These are all theoretical. They might be buildable someday with enough investment and development. But we're decades away, at minimum. More likely centuries. And even if we build them, we get tiny probes on one-way flyby missions. Not exactly the Starship Enterprise. Let's talk about what a realistic, crewed, interstellar mission would require. Because that's what people actually dream about. Not tiny probes, but humans traveling to another star system, exploring it, possibly settling there. For humans to make the journey, you need life support. Oxygen, water, food, waste recycling, radiation shielding, living space, exercise equipment to prevent muscle and bone loss, medical facilities, computers, communication equipment. A crew would need to survive for decades at minimum. More likely centuries if we're talking about journeys at achievable speeds. The concept that's been proposed for this is a generation ship. A massive spacecraft designed to sustain a community of humans for multiple generations. You launch with a crew of maybe hundreds or thousands of people. They live their entire lives on the ship. They have children on the ship. Those children grow up, have their own children, and eventually pass away, having never seen Earth or the destination. Many generations pass before the ship finally arrives at the target star system. The people who arrive are the great-great-great-grandchildren of the people who launched. The problems with generation ships are almost beyond comprehension. The engineering challenges are immense. You need a completely closed ecosystem. Every bit of air, water, and food needs to be recycled perfectly for centuries. Any inefficiency, any leakage, any failure in the recycling systems, and the ship slowly runs out of resources. The crew suffocates, or dehydrates, or starves. You need redundancy in every system. Backups for the backups. And you need to maintain all of it for hundreds or thousands of years. Parts wear out. Systems degrade. Equipment breaks. You'd need comprehensive manufacturing capabilities on board to build replacement parts. That means machine shops, 3D printers, raw materials, skilled technicians. You'd need to train each new generation in all the skills required to maintain the ship. Engineering, medicine, agriculture, manufacturing, computer programming. If knowledge is lost, if a critical skill disappears because nobody taught it to the next generation, the mission fails. The social challenges are just as daunting. You're asking people to live their entire lives confined to a spacecraft. They'll never walk on a planet. Never see a horizon that isn't the inside of their ship. Never breathe fresh air, or feel rain, or see the sun rise. They'll be born in a metal container, live in that container, and die in that container, all for a mission they didn't choose. A mission their ancestors chose for them. How do you maintain social cohesion across generations? How do you prevent conflict, rebellion, despair? How do you keep people motivated to maintain the ship and continue the mission when they'll never see the destination? What if a generation decides they don't want to continue? They can't turn around. They're in interstellar space, decades or centuries from anywhere, but they could shut down the mission deliberately or through neglect. Then everyone passes away, and the ship becomes a tomb drifting through the void. And we haven't even talked about radiation yet. Space is filled with radiation. Cosmic rays, high-energy particles traveling at near light speed, solar radiation from stars, gamma rays from distant supernovas. On Earth, we're protected by our atmosphere and our planet's magnetic field. In space, you're exposed to all of it. A spacecraft traveling through interstellar space would be bombarded constantly. The crew would need heavy shielding. And I mean heavy. Meters of water or metal or other material to absorb the radiation. That mass adds to the ship's total mass, which increases the energy required to accelerate it, which makes the propulsion problem even harder. There's also the problem of high-velocity impacts. When you're traveling at a significant fraction of light speed, even tiny particles become dangerous. A grain of sand hitting your spacecraft at 10% of light speed carries enormous kinetic energy. It would punch through metal like a bullet. The interstellar medium isn't empty. It's very sparse, but there are hydrogen atoms, dust grains, occasional larger particles. At high speed, these become a sandblaster, shredding your ship. You'd need heavy frontal shielding, which again adds mass. Some designs propose using a magnetic field to deflect charged particles, or a sacrificial shield, a chunk of material at the front that absorbs the impact. But all of these solutions add complexity, mass, and failure points. Let's consider the timing of such a mission. Suppose we launch a generation ship to Proxima Centauri. We've somehow solved all the technical problems. We've built the ship, loaded it with crew, and sent it on its way. It's traveling at 5% of the speed of light. About the maximum realistic speed for a massive crewed ship using any propulsion technology we can even theoretically imagine. The journey would take about 85 years, not counting acceleration and deceleration time. So, maybe a century total. 3 or 4 generations. Meanwhile, back on Earth, technology continues to advance. Maybe 50 years after the first ship launches, we develop better propulsion. Now we can send ships at 10% of light speed. We launch a second mission. That ship takes only 42 years to make the trip. It arrives decades before the first ship. The first crew, who've been traveling for 70 years, suddenly receive a message. Other humans from Earth are already at the destination. They got there using technology that didn't exist when the first mission launched. The first crew's sacrifice, the generations spent in transit, suddenly seem pointless. This is called the weight calculation. If technology is improving, is it ever the right time to launch an interstellar mission? Or should you always wait a bit longer for better technology that will make the trip faster and easier? The math suggests that if propulsion technology is improving at a steady rate, you should wait. You should wait until the technology plateaus, until we've reached the practical limits of what's physically possible. Only then does it make sense to launch, because you know no future mission will overtake yours. But when will we reach that plateau? Decades from now? Centuries? Never? We don't know. And if we wait too long, we might never go at all. Civilizations rise and fall. Resources run out. Political will shifts. A mission delayed indefinitely is a mission cancelled. Even if we solve all the engineering problems, even if we build a generation ship that works, even if we send it to another star and it arrives successfully, what then? The destination star might not have habitable planets. Proxima Centauri does have planets. We've detected at least 2. One of them, Proxima Centauri b, orbits in what might be the habitable zone, the distance where temperatures could allow liquid water. But we don't know if it's actually habitable. It might have no atmosphere. It might have a toxic atmosphere. It might be tidally locked, with one side always facing the star and one side always in darkness. The star itself, Proxima Centauri, is a red dwarf, a small, cool star that occasionally produces massive solar flares. These flares could strip away a planet's atmosphere or sterilize its surface with radiation. Any colony would be at constant risk. Even if the planet is marginally habitable, it probably won't be Earth-like. Different gravity, different atmosphere, different climate, different day length, different year length. Humans would need to adapt or extensively modify the environment. Terraforming, if it's even possible, would take centuries or millennia. And what if we get there and find that the planet is already inhabited? Not by intelligent life, necessarily, but by microbes or simple organisms. Do we have the right to colonize and potentially destroy an existing biosphere? Even a simple one? These are ethical questions we haven't answered because we've never faced them. There's another fundamental problem nobody likes to talk about: communication delay. Even if we establish a colony on Proxima Centauri b, it would be effectively isolated from Earth. Any message sent from the colony would take 4.24 years to reach Earth, traveling at the speed of light. Earth's reply would take another 4.24 years to reach the colony. Round-trip communication time is 8.5 years. Ask a question, and you might get an answer before you're a decade older, if you're lucky. This makes any kind of real-time coordination impossible. The colony would be on its own for all practical purposes. If a crisis emerges, Earth can't help. By the time Earth receives the distress signal and sends advice, years have passed. The crisis is long over, one way or another. The colony must be completely self-sufficient. If it can't solve its own problems with its own resources, it fails. No rescue missions are possible. No supply runs. No reinforcements. Once you commit to an interstellar colony, you're committing to permanent isolation. And that's for the nearest star, Proxima Centauri, 4.24 light-years away. Most stars are much farther. The next nearest stars are 6 to 8 light-years away. Sirius, one of the brightest stars in our sky, is 8.6 light-years distant. Distances increase rapidly from there. Within 20 light-years, there are about 100 stars. Most of them are dim red dwarfs or binary systems. Very few are sun-like stars with any hope of having Earth-like planets. To find a truly Earth-like planet around a truly sun-like star, we'd probably need to search within 50 to 100 light-years. Now we're talking about journeys that would take 1,000 years or more at realistic speeds. 50 generations on a ship. Entire civilizations born, living, and passing away between launch and arrival. The people who arrive would have no cultural connection to Earth. They'd have their own language, customs, beliefs, all developed in isolation during the centuries of travel. They'd be a separate branch of humanity, a different culture entirely. Whether they'd even still consider themselves human, in the way we understand it, is an open question. Some people propose alternatives to generation ships. What about suspended animation? Freeze the crew for the journey. Wake them up when we arrive. This is a staple of science fiction. The problem is, we don't know how to do it. We can freeze cells and embryos, and sometimes revive them. But we can't freeze a whole human and successfully revive them. Ice crystals form during freezing. These crystals rupture cell membranes and damage tissues. When you thaw, you get mush, not a living person. Some animals can survive freezing through various biochemical tricks. Wood frogs, for example, can freeze solid and revive in spring. But they're small, cold-blooded, and have specialized proteins that protect their cells. We're large, warm-blooded, and lack those adaptations. Maybe someday we'll figure out how to induce a hibernation-like state that slows metabolism without freezing. But we're nowhere close to that technology. It remains firmly in the realm of science fiction. What about sending just information instead of people? We could transmit the blueprint for a human, a complete genetic sequence, along with instructions for building an artificial womb and raising the resulting children. Send this information at light speed to a robotic probe that arrives at the destination. The probe builds the equipment, creates humans from the genetic information, raises them using AI, and establishes a colony. This avoids the need to keep people alive during the journey. The problems are obvious. We don't have AI sophisticated enough to raise children. Human development requires human interaction, especially in early years. Children raised in isolation or by machines develop severe psychological and developmental problems. We'd be creating people in an alien environment with no human caregivers, no culture, no society. Even if they survive physically, what kind of life is that? What kind of civilization would they build? There are also ethical issues. Is it moral to create people who never asked to be created, in a place they can't leave, with no choice about their circumstances? These aren't abstract questions. They're fundamental moral problems we'd need to answer before attempting such a mission. Some physicists have speculated about even more exotic possibilities. Wormholes, shortcuts through space-time that could connect two distant points. Jump through a wormhole and you emerge light years away, bypassing the vast distances of normal space. The problem is, wormholes are purely theoretical. They appear in the mathematics of general relativity as solutions to Einstein's equations. But that doesn't mean they exist. Many things are mathematical solutions that don't occur in nature. Even if wormholes could exist, they'd almost certainly require exotic matter with negative energy density to hold them open. We've never observed exotic matter. We don't know if it's possible. And even if it is, we have no idea how to create it or manipulate it. Wormholes remain science fiction, not science. What about warping space itself? The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical concept. Instead of moving through space, you contract the space in front of you and expand the space behind you. You create a bubble of normal space-time around your ship. The bubble moves through space faster than light, but the ship itself, inside the bubble, isn't moving at all relative to the space immediately around it. This gets around the light speed limit because the ship isn't actually moving faster than light. Space itself is moving. Mathematically, it works. The equations of general relativity allow for this solution. The problem, again, is exotic matter. The Alcubierre drive requires enormous amounts of negative energy, far more than we could possibly create, even in principle. Some calculations suggest you'd need more energy than exists in the entire observable universe. Others suggest you could reduce the requirements with clever engineering. But even the optimistic estimates require exotic matter we don't have. And there are other problems. Particles and radiation would accumulate at the front edge of the warp bubble during the journey. When you stop, when the bubble collapses, all that accumulated radiation would be released in a devastating burst that would sterilize anything at the destination. Your arrival would be announced by a gamma-ray blast that vaporizes the planet you were hoping to visit. Not exactly practical. Time and time again, we run into the same fundamental barriers. The distances are too vast. The energy requirements are too extreme. The speed of light is too slow and too absolute. These aren't engineering problems. These are physics problems. Laws of nature that don't bend, don't change, don't care about our desires. We can dream about traveling to the stars, but the universe has imposed limits. Does this mean interstellar travel is absolutely impossible? No, not absolutely. Tiny probes on one-way missions are probably achievable. Breakthrough starshot, or something like it, could work eventually. We could send gram-scale spacecraft to nearby stars and receive data back decades later. That's a form of interstellar travel, even if it's not what people dream about. Crewed missions to the very nearest stars might be possible in principle if we solve an enormous number of technical problems. Generation ships could work if we develop the technology, the resources, and the social structures to support them. It would require a level of commitment and resources that humanity has never mustered for any project. It would be the work of centuries, not years or decades. But it's not forbidden by physics. Just incredibly, almost impossibly difficult. For more distant stars, for any hope of creating a network of human colonies across the galaxy, for anything resembling the science fiction vision of interstellar civilization, the barriers are likely insurmountable. The energy requirements scale exponentially with distance and speed. The time scales become absurd. The isolation becomes total. We are, in all practical terms, confined to our solar system. This is a hard truth to accept. We grew up with science fiction showing us the galaxy as our playground. Star Trek, Star Wars, countless other stories where humanity spreads across the stars, meets alien civilizations, builds galactic empires. It's a compelling vision, an inspiring vision, but it's not our reality. Our reality is a universe of immense distances, absolute speed limits, and unyielding physical laws. We are almost certainly alone, not because intelligent life doesn't exist elsewhere, but because the distances are too vast for anyone to cross. Other civilizations might exist around other stars. They might be looking up at their night sky, seeing our sun as a dim point of light, wondering if anyone is out there. But we'll never meet them, never communicate with them, except possibly through radio signals that take decades or centuries to cross the gulf between stars. We'll never shake their hand, never trade with them, never learn from them directly. The stars might be full of life, full of intelligence, full of civilizations as curious and ambitious as we are. And yet, we're all isolated, trapped by the tyranny of distance and the speed of light. But perhaps there's something profound in this isolation. Perhaps it means that we need to take care of our own planet, our own solar system, because it's all we're ever going to have. Earth isn't a stepping stone to something greater. It's home, the only home our species will ever know. The solar system isn't a backyard we'll eventually grow out of. It's our entire estate. Mars could be terraformed over centuries. Venus could potentially be modified, though it would be extraordinarily difficult. The moons of Jupiter and Saturn could house colonies beneath their icy surfaces. Asteroids could be mined for resources. Space habitats could be built, massive rotating cylinders providing Earth-like gravity for millions of people. We could build a thriving interplanetary civilization right here, without ever leaving our sun's gravitational influence. Humanity could grow to trillions, spread across dozens of worlds and thousands of habitats, all within our solar system. That's not a small achievement. That's extraordinary. And it's actually achievable with technology we can realistically develop. The solar system is vast in human terms. The distance from the Sun to Neptune is about 2.8 billion miles, or 4.5 billion kilometers. That's enormous. It's 30 times the distance from Earth to the Sun. But it's achievable. Voyager reached Neptune in 12 years. With better propulsion, we could do it faster. Travel within the solar system, even to the outer planets, takes years, not lifetimes. Communication delays are measured in hours, not years. A message from Earth to Neptune takes about 4 hours. That's manageable. You can have a conversation, albeit a slow one. You can coordinate activities. You can maintain a coherent civilization. The solar system, vast as it is small enough that humanity can operate as a connected community. The stars are not. So perhaps the right way to think about our future is not as a species spreading across the galaxy, but as a species learning to thrive within the boundaries we've been given. The physics of the universe has set limits. We can rage against those limits, or we can accept them and work within them. We can build something magnificent right here, in our own cosmic neighborhood. There's a beauty in limitation. It forces creativity, resourcefulness, appreciation for what we have. If the galaxy were easily accessible, if we could hop between stars as easily as we fly between countries, would we value it as much? Would we take care of our worlds, or would we treat them as disposable, always moving on to the next one when we've used up the previous? Limitation forces us to be responsible, to plan for the long term, to build sustainably, because we can't just move somewhere else when we've exhausted our resources. The universe is filled with wonders we can observe but never touch. Distant galaxies, exotic stars, black holes, nebulas, all of it visible through our telescopes, but forever beyond our physical reach. We can study them, understand them, marvel at them. We can learn the physics that governs them. We can see the universe as it is, in all its scale and grandeur. But we do it from a distance. Perhaps that's enough. Perhaps being able to understand the universe is more important than being able to travel across it. Our minds can reach farther than our ships ever will. The laws of physics that make interstellar travel so difficult are the same laws that make the universe comprehensible. The speed of light is constant. That fact That limitation led Einstein to special relativity. Understanding special relativity led to general relativity, which describes gravity as curved space-time. General relativity explains black holes, the expanding universe, gravitational waves. All of that understanding came from grappling with the limitations the universe imposes. The same physics that traps us also enlightens us. And who knows what the future holds? Maybe in 10,000 years, humanity will have discovered something we can't currently imagine. Some physical principle we don't know about yet. Some loophole in the laws we think are absolute. It's unlikely. The laws of physics are well tested, especially at the scales relevant to human technology. But science has surprised us before. 1,000 years ago, nobody could have imagined nuclear power or quantum mechanics or general relativity. 500 years ago, nobody knew about electromagnetism or the atomic nature of matter. Our understanding grows. Maybe someday it will grow enough to reveal possibilities we currently think are impossible. But we can't count on that. We can't build our future on maybes and hopes. We have to work with what we know, with the physics as we understand it. And that physics tells us that interstellar travel is, at best, extraordinarily difficult. At worst, effectively impossible. So, where does that leave us? It leaves us here, on Earth, in our solar system, with a whole universe to observe and study and understand, with enough space nearby to spread and grow and thrive, with challenges to overcome and problems to solve right here. Climate change, resource management, energy, sustainability, political cooperation, building a civilization that can last not just centuries, but millions of years. These are worthy goals. These are achievable goals. We don't need to reach the stars to give humanity a magnificent future. We just need to take care of what we have and build something lasting. The stars will always be there in our night sky. Beautiful, distant, mysterious. We'll study them, photograph them, learn from them. We'll send our tiny probes on one-way journeys, gathering data that takes decades to return. We'll listen for radio signals from other civilizations, knowing that any conversation would span generations. We'll observe and wonder and dream. But we probably won't visit. Not in any meaningful sense. Not as a civilization. The universe has drawn boundaries. Physics has set limits. And those limits, harsh as they may seem, are part of the reality we inhabit. Understanding this doesn't diminish the universe. It doesn't make our existence less meaningful. If anything, it makes our situation more remarkable. We exist on a tiny world, one of countless worlds in a vast universe. We're conscious, intelligent, capable of understanding the cosmos that created us. We can look up and comprehend what we're seeing. We can do the mathematics, run the experiments, build the theories that explain reality. We're a way for the universe to know itself. That's extraordinary, whether we can travel to other stars or not. The physics that makes interstellar travel so difficult is the same physics that makes stars shine, that creates the elements we're made of, that governs the evolution of galaxies. It's the framework of reality, and we've figured out much of it. That's our achievement. Not building starships, but understanding. So tonight, when you look up at the stars, remember what you've learned. Those points of light are suns like ours, separated from us by distances so vast that crossing them would require energy we may never possess. The universe is beautiful and enormous and mostly beyond our reach. But it's also comprehensible. We can understand it, even if we can't touch it. And perhaps that's the real journey. Not the journey across space, but the journey of understanding. The voyage of discovery that happens in laboratories and observatories and in the minds of curious people asking questions about how reality works. That journey has no limits. Our minds can reach as far as we can see, and we can see nearly to the edge of the observable universe. The physics makes interstellar travel impossible, or nearly so, but it doesn't make understanding impossible. It doesn't make wonder impossible. It doesn't make meaning impossible. We're here, on this small world, in this vast universe. We can see the stars, but probably never reach them. And maybe that's okay. Maybe being able to understand them is enough. Thank you for joining me on this journey through the harsh realities of interstellar travel. If you found this exploration valuable, if it changed how you think about our place in the cosmos, a like or subscribe would mean a lot. It helps this channel continue exploring these deep questions about the universe we inhabit. And remember, the universe has set boundaries. But within those boundaries, there's still infinite room for wonder, for discovery, for growth. The stars are beautiful precisely because they're distant, precisely because they're unreachable. They remind us of the vastness beyond, even as we build our lives here, in the only home we'll ever know. Good night, and may you never look at the stars the same way again. There's another consideration that rarely gets discussed in conversations about interstellar travel: the sheer absurdity of the energy scales involved when you really think about them. We've thrown around numbers like 10 to the 17th joules and talked about mass ratios of hundreds to one. But let's put this in truly concrete terms that show just how impossible this is with anything resembling current or near-future technology. The most powerful rocket ever built was the Saturn V. It stood 363 feet tall, or 111 meters. It weighed 6.2 million pounds when fueled, or 2.8 million kilograms. Of that mass, about 85% was fuel. Only 15% was the actual rocket structure and payload. And all that fuel, all that mass, all that power could lift about 130,000 kilograms to low Earth orbit. 2% of the total launch mass made it to orbit. The rest was expended getting there. To reach the moon, only about 45,000 kilograms of spacecraft, about 0.7% of the launch mass. That's the rocket equation in action for chemical propulsion. You need enormous amounts of fuel to move relatively tiny payloads, even modest distances. Now imagine trying to use chemical rockets to reach another star. It's not just impossible. It's so far beyond impossible that the numbers become meaningless. You'd need fuel masses larger than planets to accelerate even tiny payloads to a significant fraction of light speed. The rocket equation spirals into absurdity immediately. Even with fusion, even with antimatter, even with propulsion systems that don't exist and might never exist, the energy requirements remain staggering. And where does that energy come from? Every joule of energy, every watt of power, ultimately traces back to the sun or to nuclear reactions. On Earth, almost all our energy comes from the sun, either directly through solar panels or indirectly through fossil fuels, which are ancient sunlight stored chemically, or through wind and hydro, which are driven by solar heating. The sun delivers, about 1.7 times 10 to the 17th watts, to Earth's surface. That's 170,000 terawatts. Enormous. But even if we captured all of it, every single photon hitting Earth, we'd need to collect for months or years to accumulate enough energy to send even a small probe to another star at meaningful speed. And we can't capture all of it. Not even close. Currently, humanity captures less than 1/10,000th of the sunlight hitting Earth. We're using about 18 terawatts of power, total from all sources. At current energy consumption rates, we'd need to collect solar energy for thousands of years to accumulate enough to send one tiny probe to Proxima Centauri. You might say, we'll build more solar panels, capture more sunlight, increase our energy production. Sure, but we're still limited by the total available energy. And the total solar energy hitting Earth, while large, is finite. We can't use more than what the sun provides unless we start using nuclear power on a massive scale. Fusion, if we master it, could help. But even fusion requires fuel, and fuel is limited. Deuterium in Earth's oceans could power civilization for billions of years at current consumption rates. But trying to accumulate enough energy to launch interstellar missions changes the calculation dramatically. You're not just powering civilization anymore. You're trying to accumulate truly enormous energy reserves to fling spacecraft across light years. The scale becomes absurd very quickly. And even if you somehow solve the energy problem, even if you build massive solar collectors or fusion reactors or tap some energy source we haven't discovered yet, you still face the fundamental physics barriers. The speed of light is absolute. Nothing with mass can reach it, let alone exceed it. As you approach light speed, relativistic effects make everything harder. Your mass effectively increases from the perspective of someone trying to accelerate you. You experience time dilation. The energy cost approaches infinity asymptotically. These aren't technological limitations we might overcome someday with better engineering. These are mathematical certainties derived from the structure of spacetime itself. Einstein's special relativity has been tested thousands of times in thousands of different ways. Every test confirms the theory. Time dilation is real. Mass-energy equivalence is real. The speed of light limit is real. These are features of the universe, not bugs in our current understanding. Unless we discover that relativity is wrong, which seems vanishingly unlikely given how well it matches observations, we're stuck with these constraints. Some people pin their hopes on wormholes or warp drives or other exotic physics that might allow faster-than-light travel. We've already discussed why these probably don't work. But it's worth emphasizing just how speculative they are. Wormholes appear in the mathematics of general relativity as solutions to Einstein's field equations. But so do lots of other things that don't exist in nature. Mathematics allows many solutions that nature doesn't use. For wormholes to be traversable, meaning you could actually go through them without being destroyed, they'd need to be held open by exotic matter with negative mass or negative energy density. We've never seen negative mass. We have no idea if it can exist. The Casimir effect produces something that looks a bit like negative energy in quantum mechanics, but the amounts are tiny and we can't manipulate them. Even if negative energy exists, we'd need enormous quantities to hold open a wormhole big enough for a spacecraft. Quantities that might require more energy than exists in several stars. The engineering challenges would make building a generation ship look trivial by comparison. and we don't even know if wormholes exist naturally anywhere in the universe. We've never detected one. We have no evidence they're real, rather than just mathematical curiosities. Warp drives face similar problems. The Alcubierre drive mathematics works on paper. You contract space in front of your ship and expand it behind, creating a wave of distorted space-time that carries you along faster than light, without you actually moving faster than light relative to the space around you. Clever, but it requires negative energy density. Lots of it. Some calculations suggest you'd need negative energy equivalent to the mass of Jupiter. Others say you could reduce the requirements with clever engineering, but even the optimistic estimates are far beyond anything we can imagine producing. And there are other problems. Hawking radiation, quantum effects, causality violations that might create time travel paradoxes. The inside of the warp bubble would be cut off from the outside universe, unable to send signals forward to steer or stop the bubble. You'd be blind and helpless inside your own warp field, unable to control it or communicate with anyone outside. And when you arrive and collapse the bubble, the accumulated radiation and particles at the front edge would release in a devastating blast. Your arrival would sterilize the destination. Not exactly helpful if you're trying to explore a habitable world. Warp drives, like wormholes, remain firmly in the realm of science fiction. Fun to think about, interesting mathematically, but almost certainly not practical, even if they're possible in principle. So, where does all this leave us? We've examined every proposed method of interstellar travel. Chemical rockets, far too slow and inefficient. Nuclear rockets, better but still limited by the rocket equation. Fusion rockets, potentially workable for slow journeys, but facing enormous fuel requirements. Antimatter, prohibitively expensive to produce. Laser, pushed light sails, might work for tiny probes, but can't carry humans. Generation ships, theoretically possible but facing massive engineering and social challenges. Time dilation helps crews subjectively, but doesn't reduce the time Earth waits or the communication delays. Exotic physics, like wormholes and warp drives, almost certainly impossible with anything resembling known physics. Every option faces barriers that range from extremely difficult to likely impossible. The conclusion is hard to avoid. Interstellar travel for humans, in any practical sense, is probably not achievable. Small, unmanned probes might work eventually. We might send tiny robots to nearby stars and receive data back decades or centuries later. That's a form of interstellar exploration, and it has scientific value. But crewed missions, colonization, building a network of human settlements across the stars, the science fiction vision of interstellar civilization, almost certainly won't happen. The physics is too unforgiving. The energy requirements too extreme. The distances too vast. The time scales too long. We are, in all practical terms, confined to our solar system. This is a profound realization when you sit with it. The stars we see at night, the countless suns scattered across the galaxy, will almost certainly remain forever beyond our physical reach. We can observe them, study them, learn from them, but we probably can't visit them. Not us, not our children, not our distant descendants thousands of years from now. The gulf between stars is simply too great, and the laws of physics too strict. This is humbling. It forces us to reconsider our place in the universe. We're not future galactic colonizers spreading across the cosmos. We're residents of one solar system, with all the space and resources we need right here, but unable to easily reach beyond this boundary. The solar system becomes our entire domain, not a way station on the road to the stars, but our permanent home. For some people, this realization is depressing. It means the end of a dream, the death of the science fiction future we imagined. No Star Trek-style exploration of strange new worlds. No contact with alien civilizations across the galaxy. No galactic empire or interstellar community. Just us, alone in our solar system, looking out at a universe we can observe but never touch. But I think there's another way to look at it. One that's actually more hopeful. Because while interstellar travel might be impractical, the solar system is enormous, and it's full of possibilities. Mars is a real world we could actually walk on within our lifetimes. It's not Earth, but it's close enough that we could potentially terraform it over centuries, create a second home for humanity. The Moon offers easy access and resources for building habitats and launching further expeditions. The asteroids contain more metals and minerals than we could use in millennia. Jupiter's moons, Europa and Ganymede, have subsurface oceans that might harbor life. Saturn's moon Titan has lakes of liquid methane and a thick atmosphere we could potentially breathe with just an oxygen mask. The outer solar system, cold and dark as it is, still offers resources and space for expansion. We could build rotating space habitats, artificial worlds with Earth, like gravity and climate, supporting millions of people in comfort. O'Neill's cylinders, several miles long, containing entire towns or small cities inside. Dozens of such habitats scattered throughout the solar system, housing a combined population of billions. We could have a thriving interplanetary civilization without ever leaving the sun's influence. An advanced spacefaring culture spanning the distance from the sun to the Kuiper Belt and beyond. That's 30 to 50 astronomical units, or about 2.8 to 4.7 billion miles. Enormous in human terms. Room for countless settlements, stations, habitats, mines, research outposts. A civilization of that scale could accomplish extraordinary things. Massive science projects studying the sun and planets in detail. Resource extraction from asteroids and comets, providing materials for continued expansion. Terraforming projects on Mars and potentially Venus, creating new habitable worlds. Space-based solar power, beaming energy throughout the system. The construction of truly vast structures, space elevators, orbital rings, even Dyson swarm components partially surrounding the sun to capture its energy. All of this is difficult, yes. All of it requires technology we're still developing and engineering on scales we've never attempted. But none of it is forbidden by physics. It's hard, but possible. It's ambitious, but achievable given enough time and resources. Compare that to interstellar travel, which physics makes almost impossibly difficult. The distinction matters. One is a question of engineering and will. The other is a question of fundamental physical law. So perhaps the right way to think about our future isn't as a species spreading across the galaxy, but as a species learning to thrive within the boundaries nature has set. The physics of the universe has given us a domain, the solar system. It's vast enough for our purposes. It contains more than enough resources to support a civilization far larger than Earth's current population. It offers challenges and opportunities for millennia of growth and exploration. And it's actually achievable. We won't reach other stars, Probably. But we can build something magnificent here, in our cosmic backyard. We can create a multi-world civilization, a network of habitats and colonies spanning billions of miles, supporting trillions of people, advancing science and culture in ways we can barely imagine. That's not a small thing. That's extraordinary. And it's within reach, if we commit to it. The limitations are real. The barriers are high. But they're not insurmountable. We can work within them. We can build a future in the solar system that's rich and full of possibility. The stars will remain distant, beautiful, and unreachable. We'll study them, wonder about them, dream about them. But our lives, our civilizations, our futures will be here, among the planets and moons and asteroids of our sun's family. That's not settling for less. It's recognizing reality and making the most of what we have. And what we have is remarkable. The universe has set limits, yes. The speed of light caps how fast we can travel. The tyranny of the rocket equation makes carrying fuel exponentially expensive. The distances between stars are measured in years and decades of light-speed travel. These constraints are real and unavoidable. But within those constraints, there's still enormous freedom. The solar system is ours to explore and utilize. The knowledge we've gained about the universe, from cosmology to particle physics to biology, is ours to build upon. The future of our species, while it may not include other stars, can still be extraordinary. So tonight, when you look up at the stars, see them for what they are. Distant suns, beautiful and mysterious, each potentially hosting worlds we'll never visit. They're beacons of light across the vast, dark, reminders of the scale of the universe. They're objects of study, sources of wonder, symbols of the unknown. But they're not destinations. Not for us. Not in any practical, achievable sense. The physics makes that clear. And maybe that's okay. Maybe our destiny isn't to spread across the galaxy, but to build something lasting here, in the one system where the laws of physics allow us to thrive. Maybe the journey isn't outward to other stars, but inward to deeper understanding, and outward only as far as the edge of our solar system. Maybe the true exploration isn't physical distance, but intellectual depth. We've learned so much already. We've figured out the laws governing motion and gravity and electromagnetism. We've understood the quantum nature of matter and the relativistic structure of space-time. We've discovered the expansion of the universe, the existence of black holes, the nature of stars and galaxies. We've learned about the origin of the elements, the process of planetary formation, the conditions required for life. We've sent spacecraft to every planet in our solar system, landed robots on Mars, put humans on the moon. We've built telescopes that can see nearly to the edge of the observable universe. We've detected gravitational waves from colliding black holes billions of light years away. We've found thousands of planets around other stars. We've done all this in barely a century of serious scientific effort. Imagine what we could learn in the next 1,000 years, the next million, if our civilization endures. The scope for discovery and advancement is limitless, even if our physical reach is bounded by the solar system. The physics makes interstellar travel impossible or nearly so. That's the conclusion, after examining all the options, working through all the math, confronting all the barriers. It's a hard truth. But it doesn't diminish the universe or our place in it. It just defines the boundaries within which we'll live and grow. Those boundaries are still vast, still full of possibility, still worthy of our ambition and our dreams. Thank you for staying with me through this long journey across the physics of interstellar travel. If you found this exploration valuable, if it changed how you think about our future and our limits, a like or subscribe would mean a lot. It helps this channel continue exploring these deep questions about the universe and our place in it. And remember, the stars are beautiful precisely because they're distant, precisely because they challenge us, precisely because they remind us of both our capabilities and our constraints. We can understand the universe, even the parts we can't reach. That's our unique gift as conscious beings. And it's more than enough. Good night. And may you never look at the stars the same way again. Let me take you through one more thought experiment that really drives home how absurd the energy requirements become. Let's imagine humanity decides, collectively, to build one interstellar spacecraft. Not a generation ship carrying thousands. Just one small crude ship carrying maybe 10 astronauts to Proxima Centauri. We want it to travel at 20% of light speed, so the journey takes about 21 years, which means one generation could make the trip. We'll use the most optimistic technology we can imagine. Perfect fusion propulsion with an exhaust velocity of 5% of light speed. We'll assume perfect mass efficiency, no wasted fuel, no structural mass overhead beyond the absolute minimum. Just the capsule, the astronauts, their life support, and fuel. Let's be ridiculously optimistic and say the capsule masses only 1,000 kilograms. The life support for 10 people for 21 years masses another 5,000 kilograms. That's absurdly low, unrealistically minimal, but let's go with it. 6,000 kilograms total payload. Using the rocket equation, with 5% of light speed, exhaust velocity, and a delta V of 20% of light speed, we need a mass ratio of about 55:1. That means we need 330,000 kilograms of fuel to accelerate. But we also need to slow down at the destination. Another mass ratio of 55:1. Total mass ratio is 55 squared, about 3,000:1. Our 6,000 kilogram payload needs 18 million kilograms of fusion fuel. 18,000 tons of pure deuterium and tritium. Where do we get that much fusion fuel? Deuterium can be extracted from seawater at about 33 grams per cubic meter. To get 9,000 tons of deuterium, we'd need to process about 270 million cubic meters of seawater. That's 270 million tons of water. We'd need to build enormous seawater processing plants, desalination facilities on an unprecedented scale, isotope separation equipment that doesn't exist. Then we'd need to breed 9,000 tons of tritium from lithium using neutron bombardment in nuclear reactors. Tritium has a half-life of 12 years, so we'd need to produce it continuously as we're building the spacecraft. Any delay in the construction schedule and the tritium decays before we can use it. Then, we need to launch all 18,000 tons of fuel into orbit. At current SpaceX launch costs of about $1,500 per kilogram, that's $27 billion just for fuel launch costs. And we haven't launched the spacecraft itself yet, or any of the construction equipment, or the assembly facility, or the crew. Double or triple that for a realistic mission cost estimate. We're talking about $100 billion minimum, possibly several hundred billion, for one tiny spacecraft carrying 10 people to the nearest star. Compare that to the Apollo program, which cost about $150 billion in today's money and put 12 people on the moon. The moon is 1,000 times closer than Proxima Centauri. The physics of interstellar travel scales the cost catastrophically. And this is with impossibly optimistic assumptions. Realistic numbers would be far worse. The spacecraft would mass more, the fuel requirements would increase exponentially, the costs would multiply. A real interstellar mission would likely cost trillions of dollars. More than the GDP of many countries. More than humanity has ever spent on any single project in history. Is it worth it? For 10 people to reach another star, spend a few years exploring, and maybe send back some data? When we could spend the same resources building permanent colonies on Mars, establishing hundreds of space stations, mining asteroids, exploring every planet and moon in the solar system. The cost-benefit analysis doesn't favor interstellar travel. Not when the alternatives are so much more practical and achievable. There's also a philosophical dimension to this that's worth considering. Why do we want to reach other stars? What's the actual goal? If it's scientific knowledge, we can learn enormous amounts from a distance. Telescopes are getting better every year. The James Webb Space Telescope can analyze the atmospheres of exoplanets from Earth orbit. Future telescopes could directly image exoplanets, see their surfaces, detect signs of life. We could study thousands of star systems without leaving our solar system. Gain knowledge about planetary formation, stellar evolution, the prevalence of life, all from here. Sure, there are limits to what telescopes can tell us. Close-up exploration would reveal details we can't see from light years away. But is that worth the cost? When the cost is a significant fraction of our civilization's total resources for centuries. If the goal is survival of the species, spreading to other stars to avoid extinction, that's a compelling argument. If Earth becomes uninhabitable, if our sun expands and engulfs the inner planets billions of years from now, having colonies on other stars would preserve humanity. But extinction risks from the sun's evolution are billions of years away. We have time. And there are closer solutions. Colonies on Mars and elsewhere in the solar system would protect against Earth-specific disasters. Asteroid impacts, nuclear war, climate catastrophe, pandemics, anything that threatens Earth alone, wouldn't necessarily threaten colonies on Mars or in space habitats. For practical species survival, diversifying within the solar system is far more achievable than reaching other stars. If the goal is simply the human drive to explore, to see what's over the next hill, that's understandable. Exploration is part of who we are as a species. But maybe the exploration that matters isn't always physical distance. Maybe exploring the quantum realm, understanding consciousness, creating artificial intelligence. These are explorations just as profound as traveling to other stars. Maybe the frontier isn't always geographic. Maybe the deepest mysteries are right here, in the nature of reality itself, and we don't need to cross light years to explore them. I'm not saying we should give up on interstellar travel entirely. If technology advances in unexpected ways, if we discover new physics that changes the equation, maybe it becomes possible. It's worth continuing to research, to study, to think about. Small-scale projects like Breakthrough Starshot are reasonable investments. Sending gram-scale probes might work, and the knowledge gained would be valuable. But massive investments in crewed interstellar missions don't make sense right now. Not when we have so much to do closer to home. Not when the physics is so unforgiving and the returns so uncertain. Better to focus on what's achievable. Establish permanent bases on the Moon and Mars. Mine asteroids for resources. Build the infrastructure for a true spacefaring civilization within our solar system. Develop the technologies we'll need for long-term survival and growth. Expand our capabilities and our knowledge. And who knows, maybe centuries from now, when we've mastered the solar system and built a stable interplanetary civilization, maybe then we'll be ready to attempt the nearly impossible challenge of reaching another star. But that's a decision for our distant descendants, not for us. Our job is to build the foundation, here and now. In the solar system, we can actually reach. Let me address one more argument people sometimes make for interstellar travel. The idea that it's our destiny, that humanity is meant to spread across the stars, that it's inevitable we'll eventually do it. This is a common belief in science fiction and popular culture. The idea that expansion is natural, that exploring and settling new frontiers is what humans do. And there's some truth to that. Humans have historically been explorers and settlers. We spread across Africa, then into Asia and Europe. We crossed oceans to reach Australia and the Americas. We settled every habitable continent on Earth. It seems natural to extend that pattern into space. But there's a crucial difference. Every previous expansion in human history was enabled by the environment. Oceans could be crossed with ships made of wood. Continents had breathable air, drinkable water, food sources, materials for shelter. The journeys were dangerous. Yes, many people died attempting them, but they were possible with the technology available. Polynesian navigators crossed the Pacific in outrigger canoes. Vikings reached North America in wooden longboats. These journeys took weeks or months, not decades or centuries. And when you arrived, you found land you could walk on, air you could breathe, water you could drink. Interstellar travel is fundamentally different. The environment, space itself, is hostile beyond anything humans encountered before. You can't breathe vacuum. You can't drink anything in interstellar space. There's no food, no shelter, nothing but hard radiation and cold dark. The journey takes decades, minimum, more likely centuries. And when you arrive, you probably find another hostile environment requiring centuries of terraforming before it's habitable. This isn't like crossing the Pacific. It's like trying to cross the Pacific while holding your breath, getting hit with radiation, dealing with equipment failures, and having no guarantee there's anything useful at the other end. The comparison breaks down. Just because humans have historically expanded doesn't mean we can expand everywhere. There are limits, even for determined explorers. No one lives permanently in Antarctica, despite it being far more hospitable than Mars. No one has settled the ocean depths, despite them being closer and more accessible than any other planet. We don't expand into truly hostile environments unless there's a compelling reason. And interstellar space is the most hostile environment imaginable. The idea that it's our destiny to reach the stars is a nice story. It's inspiring, hopeful, ambitious. But destiny isn't real. The universe doesn't care about human ambitions. Physics sets the rules, and physics doesn't negotiate. We can achieve extraordinary things within the limits physics allows. But we can't ignore those limits just because we want to. Reality doesn't bend to our wishes. The sooner we accept that, the sooner we can focus on building the actual future available to us, rather than chasing dreams that physics makes nearly impossible. One final thought about all of this. The physics that makes interstellar travel so difficult also makes the universe comprehensible. The same mathematical laws that prevent us from exceeding light speed also allow us to understand stars, galaxies, black holes, the Big Bang itself, general relativity and special relativity. The theories that set the speed limit and make travel so difficult also explain gravity, time, space, the fundamental structure of reality. Quantum mechanics, which governs matter at the smallest scales and limits what we can do with technology, also explains chemistry, electronics, the behavior of materials, everything that makes modern technology possible. The laws of thermodynamics, which make energy so expensive and entropy so relentless, also explain why stars shine, why planets form, why life requires energy, why time flows in one direction. These aren't arbitrary obstacles the universe placed in our way. They're the deep mathematical structure of reality. And that structure is beautiful, elegant, comprehensible. We've figured out so much of it already. We've gone from ignorance to understanding in just a few centuries of scientific effort. We know the age of the universe, the size of atoms, the life cycle of stars, the origin of the elements. We know how planets form, how galaxies evolve, how black holes work. We can predict the behavior of matter and energy from the quantum scale to the cosmic scale. That's extraordinary. That's a far greater achievement than traveling to another star would be. Understanding is more valuable than visiting. Comprehension is more profound than physical presence. So while the physics makes interstellar travel nearly impossible, it also gives us something better: the ability to understand the universe we inhabit, to see the patterns, grasp the principles, recognize the mathematical beauty underlying everything. We can look at a distant star and know what it's made of, how old it is, how it will die. We can observe a galaxy billions of light years away and understand its history, its structure, its future. We can detect gravitational waves from black hole collisions and reconstruct exactly what happened. That understanding connects us to the cosmos in a way that simple physical travel never could. It's a deeper connection, an intellectual and emotional bond to the universe that transcends distance. The stars remain distant, yes. Unreachable, probably. But they're not unknown. We've figured them out. We've learned their secrets. We understand them in ways that previous generations couldn't imagine. And that understanding is ours to keep and build upon. It's the real legacy of the scientific age. Not starships, but knowledge. Not colonies on distant worlds, but comprehension of how worlds form and why they're the way they are. Not galactic empires, but the mathematical laws governing galaxies themselves. That's what we've gained. That's what we'll continue to gain. And it's magnificent.